Hello, my name is Patrick Wong from University College Dublin, and I will be presenting on how the Mott transition can be viewed as a topological phase transition. First, I will review some features of topological insulators, and then I will describe how these features show up in the Mott transition. So, the SSH model is a prototypical topological insulator in one dimension. It is a semi-infinite tight binding model parameterized only by two hopping parameters TA and TB, which strictly alternate down the chain. Depending on the relative strength between these two hoppings, the system is either in a trivial phase or a topological phase. Topology can be seen in the Green's function, which for a one-dimensional tight binding model takes the form of a continued fraction, and from the Green's function, the spectral function at the boundary site. In the topological phase, the boundary is a gapped insulator, and in the topological phase, we have a band gap with the mid-gap pole. So the bulk in both cases is always insulating, so it takes the form of the trivial case, and the gap is proportional to the difference in the hopping parameters. And so that means in order to adiabatically transform from one phase to the other, the bulk gap needs to close. Some more characteristics of the topological feature are that it is localized on the boundary site of the chain, and it is robust to perturbations in system parameters. So we only require that the two hoppings strictly alternate between weak and strong and start on a weak bond. Analyzing the wave function, we see that the wave function is exponentially localized on the boundary site. Now, turning towards the Hubbard model, depicted here on the beta lattice, the relevant features that I want to highlight are the metal-insulator transition and the fact that all the dynamics due to interactions are encoded in the self-energy. Now, we note that the self-energy appears in the Green's function in the same way that a hybridization to a non-interacting bath would appear for a non-interacting system. So we use this feature to map the self-energy to hybridization in a system without interactions. So first, we take the Hubbard model and we solve it numerically exactly using state-of-the-art numerical techniques of dynamical mean field theory with numerical renormalization group as the impurity solver. So we solve numerically exactly for the self-energy. Then we take this solution and we map the Hubbard model to a completely non-interacting system, but where each site is hybridized to an auxiliary bath. And we tune the parameters of the auxiliary bath to replicate the self-energy. So the hybridization takes the form of a continued fraction, and we can determine the hybridization at each level in the continued fraction. And from this, we can determine each of the hopping parameters in the auxiliary Hamiltonian. So just to review what the self-energy looks like, in the metallic phase, you see the characteristic three-peak structure in the spectral function depicted on the top. The corresponding self-energy is depicted below as a characteristic omega squared power law pseudogap behavior at low energy. Closer to the transition, the self-energy acquires a more complicated structure at low energy, including a distinctive two-peak structure. And closer to zero energy, it still has Fermi liquid behavior. Across the transition, the self-energy has a gap with a pole at zero energy. Now, running these self-energies into our recursion method for generating hoppings, you find that in the metallic phase, self-energy produces these hoppings, and in the Mott insulating phase, self-energy produces this set of hoppings. Now we note that these set of hoppings are strictly alternating, and in the metallic phase it starts on a strong bond, and in the Mott insulating phase it starts on the weak bond. So this is analogous to the two phases of the SSH model. Having a closer look at the Mott insulating phase, we see that the wave function of the corresponding auxiliary Hamiltonian is exponentially localized on the boundary site. And we note that the set of hoppings are continuously connected to the topological phase of the SSH model. And so this can be viewed as an SSH model only with added perturbations, which do not affect the topology. Looking at the Fermi liquid side, we see that this is analogous to the trivial phase of the SSH model, where the hoppings strictly alternate and start on a strong bond. The decaying magnitude of the hoppings is what gives the pseudo-gap behavior as opposed to a hard gap behavior. Now, looking closer to the transition, we see that we have this distinctive two-peak structure where these peaks become closer and closer together as we become closer to the Mott transition, and then across the Mott transition in the Mott insulating phase, the self-energy has a mid-gap pole. So a toy model we can look at to analyze this case is an SSH model except with two poles in the mid-gap. So what this translates to in terms of hoppings is that we have an alternating pattern starting on a weak bond, but further into the chain we have a domain wall where the hoppings increase twice in a row and then return to strictly alternating. And we see as the two poles become closer and closer together, the domain wall is pushed further into the chain. Now, looking at the self-energies, we see that indeed we have an alternating behavior in the T's, and then we have a domain wall into the chain. And we have this pattern of repeating domain walls, which gives width to these mid-gap peaks. And as these peaks become closer and closer together, we see that the domain walls are pushed further and further into the chain, and the length of the bubbles also increases. And then as we make the transition into the Mott insulating phase, the domain walls are pushed effectively out to infinity, and you're just left with a strictly alternating behavior in the T's. So to summarize this is effectively a topological phase transition in the auxiliary Hamiltonian, this parametrized by the TNs. And this is a topological phase transition that does not involve bulk gap closing, but rather instead the dissociation of domain walls. We can use our knowledge of the previous to construct a toy model. So we choose a certain form of a function to describe the hopping parameters, and then upon the pseudo choice of parameters, we see that the toy model here in red matches quite closely the corresponding self-energy shown below in black. Now, characteristic of topological systems is a topological invariant, but since our auxiliary Hamiltonian does not have a translation symmetry, we cannot go to momentum space and calculate usual topological invariants, such as the Berry phase, since these are integrals in momentum space. We can, however, calculate a quantity called the Luttinger integral, where, according to Luttinger's theorem, if this quantity vanishes, we are in a Fermi liquid phase. So this quantity is equal to 0 for all interaction strength lower than the critical interaction strength for the Mott transition, and it equals 1 for all values of the interaction strength greater than the critical interaction strength. So for all values of the Fermi liquid, it vanishes, and for all values of the Mott insulator, it equals 1. So this is a promising quantity to use to parameterize the topology in our model. So this is also related to the fact that some recent work has shown that violation of Luttinger's theorem is supposedly an indicator of topological order in the system. And this quantity is also similar to topological invariants proposed by Volovic, which are functionals of Green's functions in momentum space. And we see that this quantity is dependent upon the self-energy, which is where we suppose all the topology is encoded. So some conclusions. We have shown that we can map the Hubbard's self-energy as a hybridization to a non-interacting auxiliary bath, and this auxiliary system has the properties of a topological insulator, where the phase transition corresponds to the transition between the metal and Mott insulating phases of the Hubbard model. So for some outlook, all of our calculations here were in infinite dimensions, but if we look at finite dimensional systems, the self-energy then has a momentum dependence. And then we suppose that this would imply that instead of having an auxiliary chain, we would have an auxiliary lattice. And this auxiliary lattice would still have the properties of a topological insulator. And then additionally, we suppose that if we were to perform the same strategy for superconductors, that the auxiliary bath would take the form of something resembling Majorana-Kitaev chain. Thank you for your attention.